Okay. As ever so often, I have to begin this lecture with correcting mistakes I made last time. Actually, when we calculated, well, our goal was to discuss the redshift formula in a perturbed Robertson-Walker spacetime. And actually, the expression which I derived last time was a derivative of this expression, where this is a light-like geodesic, and this is the forward velocity of our observer field. And I calculated the derivative of this with respect to the curve parameter, which I denoted by a dot. And then I calculated a while, and then a dot got lost on one term. So there was a derivative, but I just calculated the term without the derivative. And of course, the result was wrong. Yeah. So I have to correct this. I have to clean this up. So let me try to get it straight now. So I have, unfortunately, to repeat a few of the things we did last time. So the metric we were considering was the perturbed Robertson-Walker spacetime, where we have just one Bardeen potential phi. So the metric is this here, dt squared plus 1 minus 2 phi delta ij dxi dxj. That's our spacetime. That's a big bracket here. Oops. And we wanted to, well, that's the expression we need for the redshift formula. We have to evaluate this at the observer and at the emitter, and the quotient gives the redshift formula. So we need to know what our observer field is, and where with the index down, it was c squared a 1 plus phi delta mu t, delta rho t, let me write mu here, plus delta ui delta mu I. And if I want to pull the index, I need it with the index up here. So I have to multiply this with g rho mu, right? This is g rho mu times u mu. So if I multiply with the first term, the mu becomes a t. So I have gtt. Here there are no mixed terms. Let me write it this way. Delta rho t gtt. Yeah, there are no mixed terms. If mu is t, then rho must also be t. And I just get it multiplied with gtt times a 1 plus phi. And if the mu is I, then the rho must also be a Latin index. So I have delta rho j, say, gji delta ui. Okay? So that's it. And we know the metric coefficients. So this is delta rho t. This is, let me write it again, 1 plus phi. And g with the upper indices is 1 over g with the lower indices. So this is minus c squared a squared 1 plus 2 phi. Plus delta rho j. And this is just the Kronecker divided by a squared, right? Delta ji divided by a squared, because the term with the phi doesn't give anything. This is already your first order, delta ui. And here you have to be a little bit careful. I hadn't mentioned it last time explicitly. Our convention is that on the Latin indices, we use a delta for raising and lowering indices. Yeah? So if I pull this index, then this means that I have pulled it with a delta, not with a g. You have to be careful about this. And here, of course, I can expand this. So I can write minus delta rho t. Here's the a, and then 1 plus phi, and this comes in the numerator with a minus 2 phi, so it gets 1 minus phi. And I have to divide by c squared a squared, so this is 1 over c squared a. And the second term, here I pull the index, as I said, with a Kronecker, delta u j a squared. Okay, that's our rho. And then I calculated the geodesic equation, so the light-like geodesic equation. This was still correct, I hope at least. So we get, maybe I shouldn't write a dot, I should write d by ds, so that I don't repeat the mistake I made last time with a dot. Let me write d by ds. So the geodesic equation, the light-like geodesic equation, gave something like that. This was minus 2 d phi by dx. What is the speaking index rho? And then a squared c squared t bar dot squared. Yeah, so the components are t and xi, and the unperturbed t coordinate is this here, t bar. So this is the unperturbed time coordinate of the geodesic squared. Okay, and now I calculated this expression, and there I made a mistake. And in the meantime, I realized that actually it is intelligent, more intelligent, to calculate not the derivative of this expression, but rather the derivative of this term multiplied with a, because then the expressions become nicer. X mu dot u nu times a. Let me calculate this. Yeah? We are interested for the redshift formula in this expression, but if I know it with the a, then I get a nicer expression, and this is easier to evaluate. And this now I have to calculate, hopefully correctly. So I do this, of course, with the product rule. So this is d by ds g mu nu x mu dot times u nu a. Now let me continue here. Plus g mu nu x mu dot and the time derivative of u nu a. So this is what I have here, where the index is now called mu. What was rho here is now a mu. So I get minus 2 d phi by dx mu, a squared c squared t bar dot squared times u nu a. And u nu a is this here multiplied with a, this here multiplied with a. And the index is what? It's a nu. So I get this multiplied with minus delta nu t. I've multiplied with a, so the a is gone here. 1 over c squared, 1 minus v. And here I multiply with a, so 1a survives. It's delta nu j delta uj over a. That's the first term. Okay. And the second term is, let me just copy the first term and calculate the derivative here. This is d by ds of what? It's the same expression. The same expression. Minus delta mu t 1 over c squared 1 minus phi plus delta nu j delta uj over a. Okay. Actually, the first term is nicer than it looks, because this is already first order. So I see it suffices if I evaluate this to zeroth order. Yeah? I'm only interested in first order terms. This is already first order. So the first order terms here can be neglected. Yeah, because together with this they are of second order. So the only term from the square bracket which survives is here the one with the 1, the first one. F minus minus is plus d phi by dx mu a squared c squared d bar dot squared delta nu t. What is the index is it's a nu, right? It's a nu, not a mu. Sorry, this should be a nu here. Yeah, the mu is summed away, so the nu survives. The nu survives. Yes, now it's correct. So that's a nu here. Delta nu t 1 over c squared times 1. That's it. That's the first term. All the rest is negligible. Here I have first order and second order. So let me see. So I get a first order term. Oh no, this is a constant. Look, I take the derivative, but the absolute term is a constant. So this is first order with the derivative. So I have, let me write it again, g mu nu x mu dot. And here the derivative of this term gives 0. So then I get the derivative of phi times delta tau nu 1 over c squared plus the derivative of this here, delta uj over a. Now you see this is first order, this is first order, so here the zeros order is sufficient. Here's a Kronecker, gives the time derivative here, phi by dt. The c square terms go away. And then I have a squared t bar dot squared. And here I evaluate this Kronecker, so then I get a plus. So nu becomes t, then mu must also be t, because my metric is diagonal. And this is t bar dot d by ds. Phi is a c squared is constant, so I can write it in front of everything. So that's a term where I sum over this delta. And now I sum over this delta, then I get g bar with an index j here, and then the other index must also be Latin. So I have ij xi dot d by ds delta uj over a. And the nice thing which you see now is, and this would not be the case if I hadn't included the term a here, the nice thing is that this is first order. Every terms are first order. So I get to zeros order, I get just the law that this is a constant. That's the zeros order redshift law. And that's the reason why it is intelligent to include the factor a here. This makes the calculation much nicer. Okay, so I'm almost done. So I write this as 2 phi by dt. So you can't do anything with the first term. So what is g bar tt? That is minus c squared a squared, right? That is minus c squared a squared over c squared. T bar dot d by ds of phi. I could calculate this with the product rule. Phi is a function of all 4 coordinates, so I can calculate the derivative as d phi by dt dt by ds plus d phi by dx I dxi by ds. Okay? And because this is already first order, for this term the zeros order is sufficient, so I can put bars over it here, over this. So this was the middle term, and then the last term, the gij bar is just Kronecker, right, divided by a squared. This is gij bar, and xi dot bar d by ds delta uj over a. Okay, I think one term comes twice. The term with the d phi by dt here. This should be again here. Yes, this of course is the same as a dot, right? Maybe I should write it in this way. Derivative with respect to s is just a dot. So I could write it in this way, and I could here write it in this way. It's the same thing. Then I can compare these two terms, and you see it's the same term. Here it comes with a 2, here with a minus 1, so I get the term once. And then we are done. That's the final formula. Hopefully correct this time. d phi by dt a squared t bar dot squared. So 2 minus the 1 is gone, then this term is the next one, minus a squared minus a squared t bar, that's a t bar dot, right? It's a little bit small here. T bar dot d phi by dxi xi dot, and the last term, and then we are done. So ij, well, I could pull the index down again. Yeah, our convention was we pull indices with a Kronecker, So I can use this to pull the index on the u down again, if I like to do this. X bar dot dy ds delta u with an index down I divided by a. Okay, so that's this derivative which we wanted to calculate. So we observe two things. First, the term is first order. So let's denote this Q. It depends on the curve parameter S, of course. Yeah, everything depends on the curve parameter S. So the first thing is we observe it as first order. And the second thing is it involves only the unperturbed geodesic. Yeah? This is the t-coordinate of the unperturbed geodesic, t-coordinate, xi-coordinate of the unperturbed geodesic, and i-coordinate of the unperturbed geodesic. So the perturbed geodesics, the delta t and the delta xi doesn't occur. Yeah? So it's an expression which can be calculated if the perturbation is given, the phi is given, also the perturbation of the vector field. Recall, we have only used the condition that the vector field is normalized. This we have used here. But we have not used the field equation. So we have not required that it is a dust solution or a perfect fluid solution or something like that. So this can be chosen still arbitrary, actually completely arbitrary, because a normalization condition doesn't fix it in any way. And so the second observation was that this involves only the background perturbation, the phi and the delta ui, and the unperturbed geodesic. So I can, if I integrate this expression now, if I integrate this over S, then on the right-hand side, I get an integral over Q, and this can be calculated as an integral over the unperturbed geodesic. That's a crucial thing. Yeah? Oops. And this will give us a redshift formula. Oops. What was wrong last time was, first of all, I did a slightly different calculation because I didn't have the A. But what was wrong that this derivative got lost during the calculation. Last time I wrote it with a dot, and at some point the dot was just omitted. Yeah, I inserted the velocity field, but I forgot to take the derivative of it. This was wrong last time. Okay, so we can now integrate this, and then we get, we integrate this, well, it depends on the curve parameter S along the light ray, and we want to calculate, let me draw the picture again. The situation is this, we have here the emitter, here the observer, and here our light rays. So here is the fall velocity at the emission event, here's the emission event, here's the observation event, here is the fall velocity of the observer, and here's the tangent vector to the light ray. So this is x rho dot at SE, it's the emission event. The parameter S runs from here to here. It begins as a parameter value SE, E for emitter, and it terminates here at a parameter value SO, O for observer. And the quotient of these two scalar products, this will give us a redshift formula. That's what we need. And we have, with this calculation we have just done, we can write G mu nu x mu dot mu nu times A. Let me write it in this way. At the, let's say, at the emitter. Do I want to have it this way or the other way around? Let me check. Yes, exactly, yes. Minus the same thing at the observer. G mu nu x mu dot mu nu times A at the observer. This, of course, is just the integral over the thing which I have denoted Q, ds, from the observer to the emitter. So it goes backwards in time, but this doesn't matter. Yeah? So you can write it in either way. Actually, usually when we talk about lensing or travel times of light or so, we start at the observer and go backwards in time because we think I am the observer, yeah, and I look at the light rays which arrive at my position. So I trace them from my position backwards in time. Okay, we want to have the quotient of these two things. So I divide by this expression here. So I divide by G mu nu x mu dot u nu a at the observer. And then I get what? So I get G mu nu x mu dot u nu a at the emitter divided by the same thing at the observer. So I should use other indices now, because otherwise I have a little bit, I've run at the same index several times in the equation, which is not good. Then if I take this to the other side, it gives me a 1. Plus the integral divided by this expression. 1 over G rho sigma x rho dot u sigma times a at the observer times the integral. Okay, and I emphasize Q is first order. Q is first order, so it suffices to evaluate this to zeroth order. Well, let me write this a little bit more explicitly. So this is G mu nu. X mu dot depends on the parameter, so I can write SE here. And for here I write just u nu at the emitter. And A at the emitter, what does this mean? A depends only on the capital T, on the conformal time. So it means A at T, E. Yeah, the time coordinate T at the event E. Yeah? So A depends only on T, not on the other coordinates. The scale factor depends only on E, or only on T. And the same thing in the numerator, in the denominator. X rho dot SO, U sigma O, A of TO is equal to 1. And let's evaluate this to zeroth order. What is this? This is minus C squared A squared. Yeah, it's a GTT. The U has only, in zeroth order, there's only a T component. So this is T bar dot. And what was UT? The unperturbed UT. It's with the index up. The unperturbed UT was minus 1 over C squared A. Minus 1 over C squared A. And there's another A. There's another A. And this is to be evaluated at the observer. So this cancels, this cancels. And the integral is the integral. Cannot do anything with this. Well, that's our redshift formula. The only thing I have to do is I have to multiply this expression to the other side. Then I have G mu. Let me remind you, what was the general redshift formula? I proved it last time. It was 1 plus z is precisely this expression, but without the scale factor, of course. It is G mu nu x mu dot SE u nu E divided by, G rho sigma x rho dot SO u sigma O. So this here is 1 plus sigma without the scale factors. 1 plus z. So 1 plus z is this expression with the scale factors multiplied to the other side. So it gives A of TO divided by A of TE times the right-hand side of this expression. 1 plus what is left here? 1 over A squared T bar dot at the observer. How should I write this? At SO actually, yeah? Because the dot means derivative with respect to S, and I have to take this derivative at the parameter value SO. SO to SE Q of S ds. And that's it. That's the redshift formula in a perturbed Robertson-Walker spacetime of the kind we were considering. So if there's no perturbation, then Q is 0. because Q is first order. If there's no perturbation, Q is 0, so I have just the 1 in the curly bracket, and my redshift factor is just the quotient of the two scale factors. This was the redshift formula we have used in the first 2/3 of this course. Yeah? This is the redshift formula without this curly bracket in the unperturbed Robertson-Walker universe. And now we see how it becomes perturbed. It becomes perturbed by an integral over the unperturbed light ray. And the Q of S is written there explicitly. The Q of S is, where is it? Here. Is this expression. So it's given by the time derivative of the Bardeen potential, the spatial derivative of the Bardeen potential, and the perturbation of the background 4 velocity field. So this is a formula in the way as it comes out if we work with the Bardeen variables, and if we assume that we have only a scalar perturbation with one Bardeen variable. Remember, we killed the other Bardeen variable by assuming that we have a perfect fluid. This was a motivation for considering this subclass. Yeah? If you have the two Bardeen potentials, phi and psi, and if they are different, then the energy momentum tensor is not that of a perfect fluid. That's the reason why we assumed that we have only the phi. But we did not assume that this here is actually the perturbed 4 velocity of this perfect fluid. It could also be another perturbed velocity. The formula is true also more generally. So as I said, we did this for the case that we have only the phi. Sachs and Wolf, who derived this formula, or a corresponding formula for the first time. So what we have derived here is this is so the perturbation of the redshift is given by an integral over the unperturbed light ray. And this is what one calls the integrated Sachs-Wolf effect. So the photons which arrive here, which say they are emitted at a surface t equal Te, and we observe them now at time t equal To, they arrive here with a redshift. The redshift is given by this term, which would be the one in the unperturbed spacetime, and then there comes a correction term to first order, which is an integral over the unperturbed light ray, and that's what one calls the integrated Sachs-Wolf effect. So the effect of the perturbation onto the light ray, this is the integrated Sachs-Wolf effect. Of course, there would also be a perturbation in the cosmic background radiation, a deviation from the formulas we had calculated before, from the effect that already on the surface of Lask scattering the temperature is not homogeneous. Yeah? So this is sometimes called the non-integrated Sachs-Wolf effect. Yeah, the one which comes from the perturbation in the initial surface. What we have calculated here is a contribution from the integral over the light ray, and that's the integrated Sachs-Wolf effect. And as I said, we did it for this limited case where we have only the phi. Sachs and Wolf did it for an arbitrary perturbation. For an arbitrary, it was scalar perturbation, vector perturbation, and tensor perturbation. And they didn't use the Bardeen variables because it didn't exist at this time. Yeah? Bardeen was 1980, and Sachs-Wolf was 1967, I think. Yeah? So it was much, much earlier. And, but because they allowed for a vector perturbation, they had the freedom to kill the delta Ui. Yes, they could make a gauge transformation which kills the delta Ui, which set this equal to 0. But instead, they had a term for the scalar, for the vector perturbation. So in essence, it's of course the term was still there. It was reinterpreted. It was interpreted in a different way. So in their formula, it is interpreted as coming from a vector perturbation, and here it is interpreted as coming from a perturbation of the observer field. Yeah, okay, actually I had planned to work this out in more detail for a special example where we specify a solution. Here the phi is not specified yet. Yeah? find maybe any perturbation. So for instance, we could use the perturbation which I've considered, where we have Einstein de Sitter universe as background, and the perturbed spacetime is still a dust. For this we have calculated this expression, and we found that it is a term, the phi is a term which falls off with t to the power, was it 6 or 5? One of the two? 6, I think. 6, I think, yeah. So the derivative, no, the derivative had a 6 in the denominator, and then the phi, this had a 6 in the denominator. The phi itself had a 5, I think. But 5 is also a fairly big power, so it's one term which falls off very, very rapidly, and then a constant term. So it becomes constant, then this is negligible, and we have, from the potential, we have only this term, which is just, it's a spatial gradient. So it's just the ordinary, it's like in a static gravitational field, the effect on the light ray coming from a static potential. Yeah, this is, if you have a light ray moving in a static potential, for instance, in the weak field approximation of the field around a static body, then you have precisely a term of this form. So this means the photon has to climb up and down in this spatial potential, and this gives the redshift. So actually, I had planned to work this out, but time is so late because I had to repeat this now that then I wouldn't come to do anything about the Bianchi models. So I decided to leave this just to give you a flavor of how this perturbation theory is used in order to calculate effects on the redshift and not do an example, because it would take certainly 45 minutes or something like that. So I hope that this gives you, as I said, a flavor of how perturbation theory is done. So how you can calculate expressions of this sort, and where you get the perturbations up to linear order with the techniques I've used here. Okay, so I'm planning to leave perturbation theory at this point. Any questions on the perturbation theory? If not, I will now spend more or less the rest of the term with Bianchi models. So 6 is Bianchi models. So when we do perturbation theory, we allowed for deviations from homogeneity and isotropy. They could be arbitrary, so the symmetry could be completely destroyed, but we assumed that the perturbations were small, so that we could linearize with respect to the perturbation. This goes in a different direction. Here we still keep some kind of symmetry, but we allow for deviations from a Robertson-Walker spacetime which are arbitrarily big. And actually, it is possible to find exact solutions in this setting. But the price we have to keep is we have to retain some kind of symmetry. And what you retain is a homogeneity. So you drop the isotropy, but you retain you keep the homogeneity. So the idea is we have a spacetime which is still homogeneous. So no point in space is distinguished from another point. But if I am at a particular position and I look around, I see different things in different directions. So the isotropy is destroyed, or is no longer required. But why is this physically interesting? I think the main motivation why people have done this is that this allows to investigate the character of the singularity, to find out if this fact that there's a Big Bang, that all solutions we have considered in the in this theory with perfect homogeneity and perfect isotropy, that all these solutions started with a Big Bang. And the question is, could this be an artifact of the symmetries? So if I perturb the symmetry, is there still a Big Bang, or is it just an artifact of the symmetry? Actually, one could expect that it is just an artifact of the symmetry. Look, if our universe is perfectly homogeneous and isotropic, and now it collapses if we go backward in time, then what else should happen than that all these points come together? If I have perfect symmetry, everything is isotropic, so it must come together in a point. If I perturb the symmetry, so if I have, if I go backwards in time, convergence in this direction with a certain speed, and in this direction with a different speed, maybe something completely different happens. And actually, that does something different happen. That's what we will calculate now. So we will no longer have this kind of point singularities, but we will have something which is, for instance, something which is called a pancake singularity, where you have in one direction flattening, in the other direction convergence. Or we will have something which is called a cigar singularity, yeah, where in one direction everything it does not shrink to a point, but in the directions transverse to this, it comes together. So that's we can study how the character of the singularity changes if we drop the symmetry. And that's, as I would say, the main motivation why these Bianchi models are considered. So the idea is retain homogeneity but drop isotropy. So let me remind you, the Robertson-Walker spacetimes, what was the symmetry they had? And here I would then consider the Bianchi. So in the Robertson-Walker spacetime, we had the slicing into hypersurfaces. So we had a time coordinate. We could use proper time or conformal time, whatever you liked. So we have here our t lines. So this is d by dt. Let's use the ordinary or proper time along the observers. And these slices here, they are homogeneous and isotropic. And the Bianchi models, they are still sliced into hypersurfaces. We have to be a little bit careful if we can, for instance, if we consider perfect fluid solutions, if really the flow of the fluid is perpendicular to the surfaces. This is maybe not in all the cases possible to assume this. So they are so-called tilted Bianchi models. Yeah, tilted means that the T-lines are no longer perpendicular to the hypersurfaces. But in any case, we will have some kind of observer field, at least transverse to these hypersurfaces, maybe not in all cases perpendicular. And these hypersurfaces, they are only homogeneous. But in general, not isotropic, not in general. So as I said, this means if I am here or if I am here, this doesn't make any difference. Yeah, an observer here at this event will see exactly the same world as an observer here. This means homogeneity, spatial homogeneity. Of course, not space-time homogeneity. So we don't say that an observer at this event sees the same as an observer at this event. But in one of these hypersurfaces, all the points have equal rights. They are, by observations, not distinguishable from each other. But if I look into different directions here, then I see different things. And now the question is, how do we put this into mathematics? So what we have considered here was these three manifolds. Here, these slices are three-dimensional manifolds with a positive definite metric. These three manifolds had to be spaces of constant curvature. Yeah? Maximal symmetry means constant curvature. We have discussed this in some detail. So the spaces with positive, negative, and zero constant curvature. And now we have to generalize this to the general type of spaces which are homogeneous, but where the isotropy around any point is no longer guaranteed. And by the way, let me remind you, the Robertson-Walker spacetimes could be characterized by only requiring that I have isotropy around every point. Yeah, if I require isotropy about every point, then this already implies homogeneity. This was something which we encountered in the course of our considerations. So here, of course, there's no analog because we drop isotropy. So the question is, how do we mathematically characterize these three spaces, three-dimensional manifolds, which are homogeneous? Unfortunately, when people started thinking about this in the context of general relativistic cosmology, this had already been done in the mathematical literature. So they just could look it up in mathematics textbooks. And the person who did this, who characterized three-dimensional manifolds which are homogeneous, at least a certain class of them, this was this person, Luigi Bianchi. So Bianchi was not the person who invented homogeneous cosmology. He was the person who classified three-dimensional manifolds with a certain kind of symmetry. And that's what we call the Bianchi classification. And I will now briefly review this. And this was before relativity even existed. So Bianchi did this, I think, in 1890 or something like that. So he was one of the pioneers. He did the same as in the Bianchi identities, of course. Yeah? He was one of the pioneers of differential geometry. Before Ricci and Levi-Civita. Ricci and Levi-Civita started their work around 1900 or so. Okay, so our goal is to characterize, where do I write this? Oops. The case that I have spatial homogeneity, so I have a three-dimensional manifold, three-dimensional metric, positive definite metric. Yeah, these slices are Riemannian, positive definite metric. And we want to characterize the case that they are homogeneous, where symmetries in general relativity are characterized in terms of Killing vector fields. We have done an exercise on Killing vector fields. I hope you remember this. It was, I think, the second worksheet. We call symmetries of metrics are characterized by Killing vector fields. Again, a mathematician of the 19th century, Wilhelm Killing, and this time a German, actually a school teacher, if I remember correctly. So he was the first who considered symmetries in this form. So the definition of a Killing vector field so Killing vector field is something, if you write it in coordinate, it has an upper index mu, say, d mu. Or actually, in this case, we consider Killing vector fields on three-dimensional manifolds. So actually, we will have only three indices. But let me write it in general in this form. And the Killing equation, which we briefly discussed in the second worksheet, was this here. Be careful with the index down. Yeah, so what you have to do is, this is a vector field, so it's in the natural index position is with the index up. But you pull the index and then form this kind of, this combination of the symmetrization of the covariant derivative. For those of you who know what the Lie derivative is, this can be written in the form Lie derivative of the metric is 0. Yeah? Where's the metric? The metric is in two places in this equation. First, it was used in order to pull the index down. That's where the metric enters. And this, of course, is the Levi-Civita connection of the metric. So the metric, although you don't see any g in this equation, it is in this equation. It occurs here and it occurs here. So, okay, this is what one calls the Lie derivative, just for those of you who know this. I will not use a Lie derivative in this course. And, well, what's the interpretation of this equation? What we have done in the worksheet was the following. We have shown that if we have such a vector field, if it satisfies this equation, and if it doesn't have, and we evaluate this at a particular point where it does not have a 0, so k should not be the 0 vector at this point, then in the neighborhood of this point, you can introduce coordinates so that k mu becomes, or let me write it this way, k mu d mu becomes d, for instance, one of the coordinates. Yeah? So we can find a coordinate that this equation holds and that d1 g mu nu is 0. Yeah? So if you this was what we have done in the second worksheet. So if this equation holds, and if k does not have a 0, the zeros of Killing vector fields are a little bit subtle. But let's assume we are at the point where it does not have a 0. then you can find a coordinate system where the killing vector field becomes one of the coordinate basis vector fields, and the metric is independent of this coordinate. So this demonstrates that the killing equation characterizes the symmetry. Yeah? It's a direction in which the metric doesn't change. Yeah? So if you think of the flow of this vector field, you follow the integral curves of this vector field parameterized with a certain flow parameter, then you don't see any changes in the metric in this direction. So the typical example is the vector field d by dt on Schwarzschild spacetime. Yeah? Yeah, in Schwarzschild spacetime, the metric doesn't depend on the t coordinate, so this is satisfied. And the vector field which corresponds to d by dt in this case indeed satisfies the killing equation. Yeah? Because as we have shown in the worksheet, I think we have shown only one direction. We have shown that if this holds, then this also holds. Yes, exactly, because for the other direction you have to require that the k is not zero, that it doesn't have a zero. That's a less trivial and a little bit subtle point. Because of course, if it has a zero, then I cannot write it as a coordinate vector field. Yeah? So it only works if the killing vector field doesn't have a zero. So for instance, if you want to characterize rotations, then it doesn't work on the axis. Yeah? So also think again at Schwarzschild spacetime. So also if one is a phi coordinate, then also this equation holds. Yeah? The metric is also independent of the phi coordinate. This reflects the rotational symmetry about the axis. But the vector field d by d phi becomes singular on the axis. Yeah? So it cannot be written in this form on the axis. But away from the axis it does work. So this is the notion of a killing vector field, which describes symmetry as in general relativity. And with the help of this, we can now characterize the Bianchi models. So the Bianchi models, or Bianchi, how should I write this? So Bianchi classification means find all three-dimensional metrics, or classify all, that's better. Or three-dimensional metrics with three linearly independent, or let's say, with maybe I should tell you first that the killing vector fields, they have a certain property. The set of all killing vector fields has a certain mathematical structure. I should do this first, because before I tell you what the Bianchi models are. Okay, so the set of all killing vectors on an arbitrary Riemannian or pseudo-Riemannian manifold. The signature plays no role for this notion. Set of all killing vector fields. Let's call it curly K, satisfies the following properties. The first is very easy to check, actually. If K is a vector space over R, the real numbers. It is not a field over the scalar functions. What does this mean? It means that if I have a linear combination of two killing vector fields with constant coefficients, then it's again a killing vector field. If I do it with functions, then it's in general not a killing vector field. Yeah? So in mathematical technical terms, this means it's a vector space, but it is not a module over the ring of scalar functions. So this means, let me write down what this means. If I have two killing vector fields, K1 and K2, then A1, K1 plus A2, K2 is again in the set of killing vector fields for all A1 and A2 in R. And the second statement is that this is also a Lie algebra. So this includes two things. First, it says that it is a vector space. We know this already. And second, it means that it is closed under the Lie bracket. Remember, what are vector fields? Vector fields, vector fields can be defined in different ways. One way, which is mathematically the most convenient one, is that we define it as derivative operators. Yeah? Vector fields are derivative operators which act on scalar functions. If they are derivative operators, I can form the commutator. And the commutator of two vector fields is again a vector field, and the commutator is called the Lie bracket in this theory. There's a Lie algebra, and this means that if I have K1 and K2 and K, then the Lie bracket is just the commutator of the vector fields viewed as derivative operators, acting on scalar functions. That this is again in K. And, well, if you are familiar with the Lie derivatives, then this is very easy to check. If you work with this equation, then you have to calculate a little bit. And I don't want to do this on the board, but just believe me that it is true. So if I want to characterize symmetries, then I say that this algebra, this Lie algebra of Killing vector fields, should have a certain subalgebra with certain properties. That's the way in which I characterize symmetries. And that's what I will now do for the Bianchi models. So maybe for later purpose, I should also remind you that this Lie bracket or the commutator has some properties. We will need them in a minute. I think you know this. Yeah. If well, the first is obviously because let me just write this out. So this is something which is supposed to be a vector field, so I can apply it to a scalar function f, and this is defined in the following way. I first apply K2, then I get again a scalar function, and then I apply the K1, and then I do it the other way around. Yeah? What comes out is again a scalar function. So just the commutator of the operators. And I hope you all know that the commutator or the Lie bracket has two properties. K1, K2 is obvious. The first is quite trivial, it's obvious. It's antisymmetric. Yeah, it's antisymmetric. That's the first property. And the second one, which requires a little bit of calculation, but it's not difficult. Just write it out and combine all terms in an appropriate way. And then you get the so-called, what is it called? What is this identity called? Am I stupid? What's the name of this? K1. And now I permute cyclically. I need three, sorry. 1, 2, 3. I permute them in a cyclic fashion. So I have K 2, 3, 1, 2, 3, 1, and again cyclically permuted. Uh, 3, 1, 2. And this gives you has a name, but I'm really getting senile. I forgot the name of this identity. Probably I haven't written it here. No, of course not. Jacobi identity, of course. Jacobi identity. That's what it's called. Identity. So if you do, yeah?
In the first line, you have to switch the indices of the K's, right? In one. Otherwise, it's 0.
Oh, stupid, yes. Of course, the other order, yeah. So, well, when you do, if you do Lie algebra theory in a general setting, if you are not just considering this particular type of Lie algebra where you have vector fields and the commutator, you define a Lie algebra or a Lie bracket by these properties. Yeah, you say it must be a binary relation, yeah, a thing with two slots, and it should satisfy these two rules. Then it is called, and it should be linear in the entries. Then it is called a Lie bracket in general. And the commutator is an example of this. And we will use this in the following. Okay, so that was a general property of the Killing vector fields. And maybe I should also mention, I think I have mentioned this already, that something can be said about the maximal dimension of this. So it's a vector space over R, so it makes sense to ask what is the dimension. And the dimension is, the maximal dimension of K is determined by the dimension of the manifold. So maximal dimension of the Killing algebra of K on an n-dimensional manifold, let's call this dimension capital N, is n times n plus 1 over 2. So in a four-dimensional manifold, we have 4 plus 5 is 10. 4 plus 5 is 20, divided by 2 is 10. Yeah, so on a four-dimensional manifold, on a space-time in particular, I can have at most 10 linearly independent Killing vector fields. You know a manifold, a Riemannian or pseudo-Riemannian manifold, four-dimensional, where you have the maximal number of Killing vector fields? Obviously Minkowski. Yeah? Minkowski space-time has the 4 translations. The 6 Lorentz transformations gives together 10. Yeah? And the 6 Lorentz transformation can of course be decomposed into 3 boosts and 3 rotations. Do you know any other except Minkowski space-time? There are 2 more. With a maximal number of symmetries, yes. Whereas Minkowski space-time is the metric with the highest kind of symmetries which solves Einstein's field equation, vacuum field equation, without a cosmological constant. I do it with a cosmological constant. I'm sorry? Yeah, Milne is Minkowski. Yeah, it's nothing different. It's just Minkowski in different coordinates with a different slicing. But we have discussed a manifold, a space-time which solves the Einstein's field equation with a cosmological constant, and which is, in a sense, the analog of Minkowski space-time if you switch on the cosmological constant. We considered the vacuum solutions to the Friedmann equation with a cosmological constant. Vacuum with a cosmological constant. De Sitter and anti-de Sitter, of course. Yeah. These are the 3, Minkowski, de Sitter, and anti-de Sitter. Yeah. Minkowski has curvature 0. De Sitter has, in a sense, positive curvature, and de Sitter has, in a sense, negative curvature. Okay, but when we consider about Robertson-Walker spacetimes, then we are not interested in the case that the little n is 4. We only talk about the slices. And for the slices, the little n is 3. Yeah? And then I have 3 times 4, that is 12, divided by 2 is 6. So on a 3-dimensional Riemannian or pseudo-Riemannian manifold, I can have at most 6 symmetries. And that's the case in the Robertson-Walker spacetimes. Yeah? I have the 3 rotations and the 3 translations. Yeah? 3 translations, I can go in any direction, and I can rotate about any axis. So that's the maximum symmetry of the Robertson-Walker spacetime. And when we now do Bianchi models, then we drop the isotropies. So we consider slices which have not 6 symmetries, but only 3. Yeah? Only the translations. So we define, so the Bianchi classification is the following. Classify all 3-dimensional Lie algebras. Yeah, all three-dimensional Lie algebras, which then in the physical, which describe homogeneous three spaces. So this is a physical interpretation which we then use, but what mathematically is done, we just look at three-dimensional Lie algebras and classify all of them. And that's what Bianchi had done in 1890, I think, or 91 or so. So how do we do this? It's an algebraic problem, a purely algebraic problem. So the properties which we have to use is, well, first of all, that our vector space is three-dimensional, and then these properties of the Lie bracket. So the method is the following. We write or choose the basis. Let's call them K1, K2, K3 in K. So K is a Lie algebra, the three-dimensional Lie algebra we want to classify. So let K be a three-dimensional Lie algebra. And then we choose a basis. And now we have the property that if I take the base, I use now Latin indices, because I have three of them, 1, 2, and 3. So I label this with a Latin index. Okay, and this is again a member in this Lie algebra. Yeah, the Lie algebra is closed under the brackets. That's a property of the Lie algebra. So I can write it as a linear combination of the KLs with certain coefficients, which are real numbers, not functions, real numbers. CL, IJ. And they are called the structure constants of these things are called the structure constants. Of course, they depend on the basis. And they must have certain properties. Well, obviously, because the Lie bracket has these two properties, the structure constants must reflect these properties. So CL, IJ have to satisfy the following properties. So obviously, if I interchange the two lower indices, I get a minus sign. This is this rule, right? Write this here with the help of the CLs, then you see immediately this here, because this is a basis, right? I can compare coefficients. And the other one, well, this requires a little bit of calculation. I don't want to do it on the board, but if you write it out and shuffle the terms a little bit around, you will see that if you have C, let me see slowly, C, L, M, M here, exactly. And now I have I, J, K, and now I anti-symmetrize with respect to these three indices, and this can be done by multiplying with something which is totally antisymmetric. So this is 0 for epsilon ijk is what? It is 1 if ijk is cyclic. How do I write this? So it's 1, 2, 3, or cyclic permutation of this, if ijk is cyclic. Yeah, let me write it this way. It is minus 1 if this is anticyclic, and it is 0 otherwise. What means otherwise? Otherwise means that two indices are equal, right? Because they can take the values 1, 2, 3, right? So it means epsilon 1, 2, 3 is plus 1. And any cyclic perturbation is also 1. Epsilon, say, 3, 2, 1 is anticyclic. So this would give a minus 1. And every perturbation of this also. And if one of the two indices are equal, then it gives a 0. So this is a way, multiplying with this epsilon symbol is a way of saying that the expression here is anti-symmetrized with respect to the ij and the k. So that's a very convenient way of doing this. So these are the two properties the C's have to satisfy. And now our goal is a purely algebraic goal. Find all third-rank tensors, tensors with 3 indices, third-rank tensors on 3 dimensions, on a 3-dimensional vector space, which satisfies these algebraic identities. And that's the problem which Bianchi solved more than 100 years ago. And the way in which he does this, to classify, actually Bianchi did it in a different way, but the most convenient way of doing it, I think it was introduced or invented by Ellis and McCallum in the 1960s, to classify all these C, L, I, J. We do the following. Now we have a thing with 3 indices, but in this lower pair of indices there's a certain symmetry. Yeah? And I can use this in order to express all the information coded in this thing in terms of a second-rank tensor field. And the idea is the following. We introduce something which I call Tij, little Tij, which is just C, how do I do this? It is just epsilon, I, J, K, C, I should use different indices. Let me start with the right-hand side. C, L, I, J, and now I multiply with M, I, J. And then I get something which has M and L as speaking indices. That's it. So by multiplying with the epsilon symbol, I don't lose any information because this is antisymmetric in these 2 indices. If I had something here without this symmetry, if CLIJ would not be antisymmetric in the indices I and J, then I would lose information by multiplying it with these things because the symmetric part would then drop out. But if it doesn't have a symmetric part, then I don't lose any information. And now the goal is just classify all second-rank tensors on a 3-dimensional manifold, which of course much easier than classifying third-rank tensors with a certain symmetry. Yeah, but it is equivalent. And yeah, how would you classify second-rank tensors? This is matrices, right? A second-rank tensor is just a matrix. How would you classify all matrices? Well, obvious idea is decompose it into symmetric and antisymmetric part. Yeah. So the TML is then written as a symmetric part, Nij, which is the same as Nji. Yeah, it's a symmetric part plus an antisymmetric part. And the antisymmetric part can again be written with the epsilon symbol times AK. Yeah, that's the general form of an antisymmetric second-rank tensor. It must be a covector multiplied with the epsilon symbol. And now it looks pretty simple. So we have really reduced the problem to a much, much simpler problem. We have to classify the symmetric second-rank tensors. That's very easy. You know this. This is metric tensors, yeah, which may be degenerate. Classification of metric tensors. And yeah, this is just a 3-component thing which can be fairly easily classified. And that's what we... Yeah? Oh God, of course. Sorry. Okay, and well, it's fairly obvious that there are 2 subclasses now. They are called Bianchi A and Bianchi B, depending on whether or not this is 0. Yeah? So if this is 0, then it's very easy. These are the Bianchi type A models, and I will begin with them. And then I consider Bianchi type B, which is a little bit more subtle. What is not quite clear is whether these things are independent. And actually they are not independent because we have these identities. Well, we have already taken care of the antisymmetry of the CLIJ because this enters into the definition of the TML. Yeah? We have already used that this is antisymmetric, but we have not yet used the Jacobi identity. And the Jacobi identity actually gives the gives a relation between the Nij and the AK. So I have to, this is a restriction we have to keep in mind. I'll write it down in a minute. See if I can get this dry quickly. Okay, so can I squeeze this here? Maybe here. So with a little bit of calculation, you see that's the Jacobi identity. That's this here, this identity. Yeah. So you have to express the left-hand side in terms of the t's, and then see what it gives for the n and the a. There you need the formula for the epsilon symbol. If you multiply an epsilon symbol with indices down and indices up, there are certain rules for evaluating this, which we have to use. And if you do this, so it's not one line, it's a few lines, but what you get in the end is that requires, or is actually equivalent to the condition that Nij, Aj must be 0. Yeah? So the Aj is in the kernel of the n. So if the A is non-zero, then the n must have a kernel. So it cannot be non-degenerate. Okay, I don't calculate this on the board. And I think it's also boring to do this as an exercise because it's just algebra. Okay, and now we can we say that Bianchi class A. These are the solutions with AI equals 0, and Bianchi class B. These are the ones with AI non-zero. By that I mean they are not all 0. So maybe I should write it more clearly in this way. A1, A2, A3 is not 0, 0, 0. Yeah? At least one of the components of the A must be non-zero. Then we say it's class B. And class A can now be immediately classified. So class A. So what are the possibilities? We can, the n is symmetric. So if it is symmetric, we can diagonalize it. Yeah? Every symmetric matrix can be diagonalized just by choosing the basis appropriately. Of course, we can choose a basis in our Lie algebra as we like. And if we do this appropriately, we get just, so for Nij is N1, N2, N3. So we can achieve this. And then we can also stretch or shrink the length of the axis. So if these things are non-zero, we can make them to plus or minus 1. Yeah? That's the usual thing when you classify metrics. That's the reason why you have to consider only the signatures where you have ones and minus ones in the diagonal. Yeah, because you can rescale the length of the basis vectors. So the cases we have to distinguish are only the cases that these things take the values 0, 1, or minus 1. Can be 0, of course, yeah? Because we don't know if this thing is non-degenerate. And now I can write down the table for the class A. So I have the values A1, N1, N2, N3. Of course, the first possibility is that it is just a 0 tensor. Yeah? that all of them, that all the n's are 0. Then I have the case I have to be careful with the order, so that I have them in the same order on the board as they are usually written. So now comes the case where I have a two-dimensional kernel, and because, well, instead of multiplying with the epsilon, I could also multiply with minus epsilon, and then I would get a minus sign here. So if I have in the third component, so let's assume two of them are 0, I have a two-dimensional kernel, then if I have a +1 or a -1, this is not an intrinsic difference. As far as the algebraic structure is concerned, it's the same thing. So I can just restrict to the case with a +1. Then I have the case that I have a one-dimensional kernel. And then the other two could have different signs, 1 and -1. And the other two could have the same sign. And then again, I could, without loss of generality, arrange that it is a positive sign. And of course, a case that all of them are different. So I have the case that which comes first with a -1, that it has Lorentzian signature, and the case that it is positive definite, 1, 1, 1. And these are all the cases which can happen. And well, Bianchi made the classification in a slightly different way. That's the reason why the terminology is now a little bit odd. So this is called Bianchi type 1. This is called 2. Now you would expect that it goes on with 3, 4, 5, and so on, but that's not the case, because, as I said, Bianchi introduced these classes in a different way. This is called 6, 0. We will see in a minute where this terminology comes from. This is called 7, 0, and that's 8 and 9, right? Yes. 8 and 9. So these are the Bianchi types which form the class A. And of course, this is the simplest, and we will consider this in detail then next time. Yeah. So we'll consider the case. What does this mean? We have class A, so the little a is 0, and we have also the n's equal to 0. This means the structure constants are all equal 0. Yeah. This means that our killing vector fields commute. Yeah. It's a trivial Lie algebra. It's a Lie algebra where the bracket is a 0. So that's in what is called an abelian Lie algebra. And this case, of course, is the simplest one. And we will discuss the solution to the field equation then next time for this class of solution. This will give us the Kastner solutions and related things. And also a special and interesting case is this here. Bianchi 9 is also interesting. The Lie algebra, which is here reflected by this standard form of the structure constants, is the Lie algebra of the rotation group of the SO3. Yeah, so that's the SO3 Lie algebra. This is three-dimensional, of course. Yeah, there are three rotations, and they form a Lie algebra. So the generators form a Lie algebra. So SO3 must be included in this classification, and this is this here. And there are also famous solutions to the field equation for the Bianchi 9 case. These are, for instance, the Orschwald-Schücking space-time, which, if time permits, I will also briefly mention. Okay, so this is class A. Now comes class B. This is more complicated. Class B is more complicated because when we scale the well, first of all, in this case, the n must have a kernel. So one of the three n's must be 0, yeah, because of this identity. Yeah? If the A is non-zero, then this means that the n has a kernel. So it must one of the three n's must be 0. So then you would say, okay, fine, then I can rescale the other two. This is an Nij with upper indices. If I transform the other two basis vectors, this also affects the basis vector for the AK, which transforms with the inverse matrix. Yeah. So I cannot rescale them independently. So I cannot say I set one of the components of the A equal to 1, and simultaneously the remaining two n's also equal to 1. This is not possible in all cases, and that's the reason why in the class B case we don't have these discrete classes. We have also a continuous class, which depends on a continuous parameter, where we cannot scale the component from the A equal to 1. But of course we can In this case, so we can make one of them equal to 0 because it has a one-dimensional kernel. Which one? The first? Yes, the first one. So we have a 1 here. So we have only n2 and n3. And the AI, there we can arrange that this has only a component in the first, something different from 0 in the first component. But we cannot scale this to plus or minus 1 and this to plus 1 simultaneously. Not always, not in all cases, because the transformations are dependent, right? This transforms with a certain matrix Lij, linear transformations, and this with the inverse. And if I transform two of the x's with a certain matrix, then the other x's will be affected by the inverse. Okay, so what we get is, so I have here the A, n1, n2, n3. Oops. So here I have, let me begin with this here. So again, I have the case that all three of them are 0. And this is 1. Then we have the case that one of them is 0. And the third one can then be chosen to be plus 1. In this case also I have no problem with the rescaling, so I can make this equal to 1. It only occurs if I scale 2 of the spatial axis. And yeah, then it happens. If I have these two cases with plus and minus, and with plus, it's not in general possible to make the A equal to 1. And it depends on whether we have something, so the H is A over N2, N3 if N2 and N3 are different from 0. Of course, I cannot introduce this if they are 0, and then I don't have to introduce it. So this H can be positive or negative, and then it gives these possibilities. Okay, and this is called Bianchi type 5. This is called Bianchi type 4. This is called 6H, where H is this continuous parameter, and H is positive. And this is called 7H, where H is negative. And yeah, well, now you see why are they here called 6-0 and 7-0, because they correspond to this case here, where the H becomes 0. Yeah, that's the reason why they are labeled in this strange way. And if you look at all the numbers, you see that 3 is missing. Yeah? Whereas type 3, well, type 3 is actually contained in these two. So type 3 is the same as type, it was 6 minus 1, yes. Type 6. Oh, I wrote it the wrong way around. Look, of course, here H is negative, here it is positive. Yeah, if H is positive, then I couldn't take the square root. It's just the other way around. So this can take the value minus 1, and that's exactly this case here, 6 minus 1. Yeah, as I said, Bianchi introduced the classification from 1 to 9, and he did it in a different way. And now in this modern rewriting of his result, we have these cases with a continuous parameter, and then type 3 is just a special case of these types, 6 and 7. That's why the terminology looks a little bit odd. So these are the Bianchi classes, and what we will do next time, we will look at one particular of them, the simplest type, and we will solve the field equation for this. So we will write down a metric which has this symmetry, which has Bianchi 1 symmetry, means a abelian Lie algebra of Killing vector fields which generates homogeneous transformations on the 3 spaces, and we will solve the field equation for vacuum and for a dust. And for vacuum, this will give the fairly well-known Kasner solutions with the pancake singularity and the cigar singularity. Okay, so I hope that I can do this next Friday. Any questions to this? Okay, then let's see you on Friday.